Welcome to the Chapter 9 Part 2 video. This video will cover 9.4, 9.5, and 9.6. It is very important to understand the first part of Chapter 9 before starting this video. So if you have any questions on the three types of rigid motions that we've talked about, which is translations, rotations, and reflections, come back to the Zoom room and ask your questions first, because otherwise this section will be very difficult. So our objectives for 9.4 are to find compositions of isometries, which we'll talk about in a second, including glide reflections, which we will define on this page, and to classify the isometries. So what is an isometry? An isometry is a transformation that preserves distance or length. Therefore, translations, reflections, and rotations are all isometries. We have been using rigid motion to describe this same thing. So what does it mean to compose transformations? Well, recall in algebra, we had function compositions where we had f composed with g of x, for example, which we would say f of g of x. And what that meant is that we had two functions. We would perform one function, the one on the inside, and then we would immediately perform a second function. And so, for example, I might say x plus 2 and then x minus 7. And I would just do both of them in a row, and I would get one solution. Well, a composition of transformations means that I'm performing multiple transformations in a row. So this is performing or completing multiple transformations in a row. So the warm-up that we did today was a composition of transformations. You did one, and then you did the next, and then you did the next, until finally we got a result. So what does it look like when we compose some of these transformations? Well, if we're looking at a reflection across two parallel lines, so if I reflect across a line and then I reflect across a line that's parallel, what we end up with is actually a translation, right? So think about if I have a triangle, I reflect it, and then I reflect it back. So this triangle actually just moved over. This is a translation. So two reflections across parallel lines ends up giving you a translation. What if those lines are not parallel? Then we would have a composition of reflections across intersecting lines. If I take a triangle, reflect it over here, then reflect it over here, well, it wasn't just sliding, right, because it turned. And so that is a rotation. And our last type of isometry that we're going to talk about is called a glide reflection. So any composition of isometries can be represented by a reflection, rotation, translation, or a glide reflection. And just like it sounds, a glide reflection is where there's some sort of translation and a reflection. And together, a translation and a reflection can't be simplified into one of the other three. So this is our fourth type of isometry. Let's look at what a glide reflection is. So first, we're going to look at this notation. We're transforming segment CD, and we're doing two transformations here. We're doing a translation as well as a reflection, right? Capital R for reflection. And so first, what we're going to do is identify the coordinates of the given points. C is at 1, 3. D is at 4, 5. And then we'll translate first. So I'm translating by this vector here, -4, 0, x, y. So this is going to the left by 4, and it doesn't go up or down. So I'm just going to slide this right over 4 units. 2, 4, there's C prime, D, 2, 4, there is D prime. So what are those coordinates? Well, this is at -3, 3 now, and D prime is at 0, 5. And then we're going to reflect it, reflecting it over the x-axis. So how far is C prime from the x-axis? 1, 2, 3 units. 1, 2, 3 units to get C double prime. Same thing for D prime is 2, 4, 5 units. 2, 4, 5 units to get D double prime. Our coordinate for C double prime is -3, -3. And for D double prime is 0, -5. Now, normally when we compose functions, we will, or compose transformations, we will compose them the same way that we compose functions. So if I have a translation composed with a reflection, what I should do is I should reflect first and then translate. So let's look at another example. The reason I did this one in this order is to show you kind of the steps of doing the composition of transformations. What I want to show you in this next example is the order. So let's look at the next page. So for this example, we want to reflect the triangle across the line x equals 1. That's a reflection across the line x equals 1, followed by a translation 1 unit to the left, that's -1, and 4 units up is a +4. Left and up. Okay, but the question is, what order should we do this in? So if I'm doing the reflection first, that's going to be my second step. I'll have the pre-image, I'll have the reflection, and then I'll have the translation. And when we write our composition, it's going to go reflection on this side and translation on this side, because we always start with the one on the right. I'll explain that in a little bit more detail after we do the transformations. So first we're going to reflect across the line x equals 1. We need to find that line. Here's where x equals 1. Here is our line of reflection. T is on that line, so it will stay where it is. S will go 1 unit away. U is 3 units away. S prime, U prime, T prime. And then we want to translate 1 unit to the left and 4 units up. So I'll take S prime, 1 unit to the left and 4 units up, get S double prime. T prime, 1 unit to the left and 4 units up, there is T double prime. And U, 1 unit to the left and 4 units up to get U double prime. And now let's fill in some of these coordinates. So our pre-image, the original S, starting from the origin, that is 2, 0. T from the origin is 2, -1, -3. U from the origin, that is 2, 4, -4. And then after the reflections, we get S prime, T prime, U prime. S is at the origin. T is 1, -3. And U, -2, -4. And then after the translation, S double prime, T double prime, U double prime. S is at -1, 4. T double prime, 0, 1. U is at -3, 0. Okay, so why do we write the reflection and then the translation in this order? Why are we reading it from right to left instead of left to right? Well, again, think back to those function compositions. In algebra, we say f composed with g of x is the same as f of g of x. Well, order of operations says I have to perform what's inside of the parentheses first, and g is further inside of parentheses than f of x. Okay, so imagine if I have f of x equals 2x and g of x equals x plus 1, then f composed with g of x will be f of g of x, where g of x is going to replace g of x here. So now we have f of x plus 1. Well, when we perform our function f now, we're substituting this whole thing into x. So this becomes 2 times the quantity of x plus 1. Okay, so what order did we do this in? Well, we did g of x first and f of x second. So the same thing goes for transformations. This will be second, and this will be first. Okay, let's take a look at 9.5. In 9.5, we're looking at how do we use these compositions in order to verify when objects are congruent. So our objectives are to identify congruence transformations and to prove triangle using isometries, triangle congruence using isometries. So 2 figures are congruent if and only if there is a sequence of rigid motions that maps one figure onto the other. If and only if means we can do it backwards as well. If they're congruent, then I should be able to map one onto the other. I should be able to move one using all of these isometries to put it directly on top of the other. Okay, so when we're doing this, when we're proving congruence or using congruence to write these transformations, it's called congruence transformations. Not a very creative name. The image on the right shows that the composition of our parallelogram, or quadrilateral rather here, L, M, and O, can be reflected and rotated. So we're looking at our original and our final shapes here. We want to list all pairs of congruent angles and sides. Okay, well, let's look at this angle right here. Was rotated and then it was reflected. So angle O is congruent to angle K. Then we'll look at angle L, was rotated and then reflected. So angle L is congruent to angle G. And then angle M, rotated, reflected. Angle M is congruent to angle H. So see, we're pulling in skills that we've been building up throughout the year. Angle N, here, here. Angle N congruent to angle J. And now we can do the sides. So we'll say OL is congruent to OLKG. LM, GH. So I'm using the angle statements that I have in order to write my segment statements. MN, HJ, and then finally NO with JK. All right, and the next example, identify congruent figures. Which pairs of figures in the grid are congruent? Well, let's start with our segment here. This segment has a length. We could make a little triangle here. 1 and 3. With Pythagorean theorem, we could find its exact length, but really just the 1 and 3 define that length. So if we go to this segment here, 1 by 3, also the same length. And so we can say that PQ segment is congruent to segment HG. We have 2 triangles here. Are they congruent? Well, we know this is a right angle. This side length is 4. This side length is also 4. So that's an isosceles right triangle. This side length is 4, and this side length is also 4. So those triangles must be congruent by SAS. So we can say triangle EDF is congruent to triangle. Well, E is one of my isosceles bases. So that is N. D is my right angle. I need a right angle is L. and then n is left over. And then finally, our trapezoids here. How do I know that they're trapezoids? Well, I know that these two lines are parallel because they're both on horizontal lines. This is also a trapezoid, so that's a good start. The base here is 2. The base here is 5. 2, 5, 2, 5. Then I can say this segment is 2 by 2. This segment, so this segment is 1 by 2, doesn't match. 2 by 2, that matches. And this segment is 2 by 1, 2 by 1. This segment matches. So then we can say quadrilateral, the x, w, z, y is congruent to. Now we got to make sure. X is 2 with 3 marks. 2 with 3 marks is B. W, 2 with 2 marks. 2 with 2 marks is A. Z, 2, 5. 2, 5 is J. And the last one is Y. The last one here is C. Okay, so again, very important to write your congruence statement exactly. The next question, what sequence of rigid motions maps A, B, C, J, that's the quadrilateral, to this other quadrilateral? Okay, well, notice the long side of my quadrilateral is on a different side. So that tells me that I'm going to need a reflection. Okay, so let's take, we started with A, B, C, J. We're going to take A, B, C, J, and let's reflect it. What do we want to reflect it over? Well, if we reflect it this way, the long side would be on top. We don't want the long side on top. We still want it on the bottom. So we need to reflect it over the y-axis. Reflect over the y-axis. That's not all we're going to do, so I'm going to put a little composition symbol. So if I reflect this over the y-axis, and I'm going to switch colors, I get here C, B, A, J. And now I want to translate it onto our other quadrilateral there. So in order to translate this, I need to go up and over. That's up 5 and over 1. Okay, so up 5, left 1. Well, when I write that as a translation, it's going to be a translation by some vector. Always go horizontally first, x, then y. So this is to the left is -1, up is +5. So that is our other composition. And if the corner matches there, and I know the shapes are congruent, then we're done with our transformations. -1, 5. Okay, now because this is a slide or a translation and a reflection, this is a glide reflection. Let's take a look at the next example. In the previous diagram, what transformations take triangle DEF onto triangle LMN? So here we have triangle DEF. We want it to go down here onto triangle LMN. Well, one of the nice things about isosceles right triangles is that I can rotate this and I don't have to worry about reflecting. If I did a reflection, if I wanted these 2 points to reflect over here, D would be on the wrong side, right? If I take this triangle and I flip it here, it would make a triangle like here. So what I want to do is I want to actually say what will take this triangle and put it down here, but also with my right angle at the top. Okay, so what will take this triangle and move it here? That's going to be a rotation, right? I take this, in order for D to turn onto the top, this has got to be a rotation. So I can see that these points are around the origin. I'm going to say this is a rotation. It's rotating about the origin. How far does it have to rotate? Well, from F to N, that makes a straight line. So that's 180 degrees. I can also check with the vertices. from D to L, again, through the origin is a straight line, so that is 180 degrees. And notice it's 180 degrees whether I go clockwise or counterclockwise, and 180 is the only number we don't have to worry about that. And lastly, in our diagram, what composition can map ABCJ onto WXYZ? Well, luckily, because of the way we wrote our rigid motions before, we can just copy that answer right down here. We already wrote it as a composition. So the translation by -1, 5 after a reflection over the y-axis of, what did we start with? A, B, C, J. Let's take a look at our next example. In this example, we have triangle JQV and triangle EWT. They already told us that these two triangles are congruent, which means I should be able to transform this triangle onto that triangle. This congruence statement is going to help us determine what transformation to perform. So, for example, I have J corresponding with E because those are the first letters of my congruence statements for each of those triangles. So that tells me J should map to E. Okay, so that tells me this is not going to be a reflection where J reflects onto W because those are not the vertices or the angles that correspond. Okay, so then we want to say Q maps to W. Okay, well, Q to W, it's not going to be a translation because that would map Q closer to T. In order for this, see how J and Q go down and to the left, E to W goes down and to the right. Because those are opposites, I need a reflection. So that tells me I'm going to need a reflection. Okay, what am I reflecting? I started with triangle JQV. And what do we want to reflect across? Well, I find it easiest to just always reflect across an axis. So I'm going to take triangle JQV. I know I need to reflect it, so I'm going to go ahead and reflect it over the y-axis. Just like before, why did I choose the y-axis? Well, if I reflect over the x-axis, J will be underneath Q. Remember, J and E correspond. Q, let me get a different color. Q and W, V and T. And I know that from my congruence statement. And so I know that I want blue over pink, blue over pink. If I reflect it, pink will be over blue. But I do want pink to the right of blue, so I want to reflect it this way. So I take Q moves there, J goes there, V, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So here's my new triangle. This is blue, this is pink, and this is orange. So how do I move my green triangle now? Well, to get pink on pink, I have to move it up, blue to blue, orange to orange. Those should all be exactly the same. 2, 4, 5. 2, 4, 5, 2, 4, 5. So I reflected over the y-axis, and after I did that, I slid it, translate, by some vector. Horizontally, nothing. Vertically, up, positive, 5. Let's look at section 6. This is our last section for chapter 9, and this is a new type of transformation. This is not an isometry. So remember, we had 4 types of isometries. We had translations, also called slides or glides. We had rotations, reflections, and then we had glide reflections, which took a combination of a glide and a reflection. So our new type of transformation is a dilation. So think about dilating. Dilating means getting bigger or smaller, okay? So think about when you go to the eye doctor, for example, if you're getting an eye exam, they put special drops to dilate your eyes so that they can see inside through the pupil, okay? So dilation means changing size. And specifically, it means getting smaller or bigger without changing your ratio. So this is going to give us similar figures instead of congruent figures. So our objective is to understand dilation of images and figures. So remember, a rigid transformation, we just talked about this, is a transformation that does not change size or shape, and this is an isometry. And so our rigid transformations, we said, are translations, which is movement up, down, left, and right. We have reflections, which is a flip, and we have rotations, which is a turn. A non-rigid transformation is a transformation that does change size or shape of a figure. A dilation with center of dilation C and a scale factor of n can be written by dilation by n at C. So we say, this is how much it's changing, and this is where it's changing from. The scale factor of a number is the number that is multiplied to enlarge or shrink a figure. Enlarge, make it big. Shrink, make it small. What scale factors would enlarge a figure? Well, enlarge, making it bigger, means we need to multiply it by a number that will make it bigger. So a scale factor greater than 1 will make the figure larger. Which scale factor will reduce a figure? Also shrink or reduce is the number that will make it smaller. That is something less than 1. Think about if I multiply something by a half, it gets smaller. If I multiply something by 7, it gets bigger. What scale factor will produce a congruent figure? Well, if it's not bigger or smaller than it's congruent, that is a scale factor of 1. Let's see some examples. In this example, we want to dilate the rectangle ABCD, use the origin as the center, and a scale factor of 2. So how we do this is we say, from the center to point A, I went a distance across by 1. Now, if I use trigonometry or I use my special triangles, I can find exactly the distance to A, but really, I don't need the number of the distance. I don't need the value. I just need to know how to double it. So if I went diagonal by 1, I'm going to go diagonal by 2 to get A prime. For B, I go diagonal this way. So that was across 4 over 1. To do that same distance again, I can go across 4 over 1 in the same direction to get B prime. So really what I'm doing is I'm drawing the distance and then I'm copying it again. From the origin to point D, I go up 3 over 1, up 3 over 1 again gives me D prime. To point C here, I go over 4, up 3. Again, I need to do that same movement, over 4, up 3 to get C prime. Now notice my resulting figure is much larger than my original figure. What really happened is I took this and I doubled its size, but I also doubled the distance that it is from the origin. So if we look at our original rectangle, it was 2 by 3. Our result is actually 4 by 6. Let's write down the ordered pairs. A went from 1, 1 to 2, 2. B went from 4, 1 to 8, 2. C went from 4, 3 to 8, 6. So really, when we're doing this from the origin, I'm multiplying every part of the point by 2. D goes from 1, 3 to 2, 6. Let's try it with the next example. Dilate triangle TRI from the origin using a scale factor of 1/3. 1/3 should shrink. So we'll start with point T. Point T is already 0 units away from 0. If I multiply that by 1/3, it's still 0. T is not going to move. So T stays in its place. The point that is the center of dilation never moves. I, though, is 2, 4, 6, 3 away. I need to divide that by 3. So I'm going to take 6 divided by 3 is -2. And then 3 divided by 3 is 1. -2, 1. So what I've done is I've split this into 3 pieces, and gone just one of those lengths. So point I prime is -2, -1. And again, if I took the point of the pre-image, multiply it by the scale factor, I will get the point of the image. So using that same idea, here is R. I take 6, -3 times 1/3. 6 times 1/3, 6/3 is 2. -3/3 is -1. 2, -1. And again, that only works when the center is the origin. Let's take a look at a few more examples. For number 3, we want to dilate the quadrilateral QUAD, dilating N center. So this is our scale factor, and this is the center. Just like with rotations, if it's a 0 or an O, that means the origin. O is the origin, which is 0, 0. So we're, again, dilating from the origin by 1/2. So this should shrink. So this, from the origin to U, I go 4, 2. Cut that in half is 2, 1. There is U prime. From the center to Q, that is 6, 4. Cut that in half is 3, 2. Again, I'm just reading distances. So I'm not saying that this is 6 units on a number line. I'm saying it has a distance of 6 units. To point D, this is 6 units, half is 3. Across is 4 units, so half is 2. Again, a distance, D prime is half of the distance to D. So it's the midpoint between D and the origin. And then A, 6 units, 2 units, half of that is 3, 1. There is A prime. And so we get this quadrilateral that is similar to our original quadrilateral, but half as big. So for our points of the image, dividing each of these numbers by 2 or multiplying them by 1/2, we get -3, 2, 2, 1, 3, -1, -2, -3. Just taking half, 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 half. Let's look at number 4. Triangle NGI, dilating, scale factor of 2 should enlarge. About the origin. Okay, so this time we go 3, 2. Instead of cutting it in half, we're doubling it, so that goes up again, 3, 2. There is N prime. G, 5, 4. Do it again. 5, 4. Doubled it. G prime. I, -2, 5, -2, 5. Again, I prime. So all I did is I'm going a certain distance, and I'm going that same distance again. Here is our resulting triangle. Okay, so again, angles are going to be the same, but the side lengths are proportional. This is a similar triangle. To find the coordinates of the points, because I'm centered at the origin, I can just multiply each of these by 2. -2 times 2 is -4, 3 times 2 is 6, 5 times 2 is 10, 4 times 2 is 8, Negative 2 times 2 is negative 4. Negative 5 times 2 is negative 10. I'd like you to try example 5. Triangle WUN is dilated using the origin as the center of dilation and a scale factor of 5. What are the coordinates of U prime? So you only have to dilate 1 point for this one. So the first step here is going to be finding the coordinates of U, which are 1, negative 3. Scale factor of 5, so I'm multiplying times 5. U prime gives us 5, negative 15. That is going to be option B. For number 6, we have quadrilateral RAPS with the vertices given. It's dilating using the origin as the center with a scale factor of 2/3. Find the coordinates. So I'm going to write them here. RAPS, negative 6, 4, negative 12, negative 9, negative 3, 6, 15, 24. To find R prime, I take negative 6 times 2/3. Times 2/3. All of this times 2/3. Well, I'm going to do divided by 3, then times 2. Negative 6 divided by 3 is negative 2, times 2 is negative 4. 4 times 2 is 8. I can't divide it by 3, that's 8/3. A prime. Negative 12 divided by 3 is negative 4, times 2 is negative 8. Negative 9 divided by 3 is negative 3, times 2 is negative 6. P prime, negative 3 divided by 3 is negative 1, times 2 is negative 2. 6 divided by 3 is 2, times 2 is 4. S prime, 15 divided by 3 is 5, times 2 is 10. 24 divided by 3 is 8, times 2 is 16. Without having to graph anything, we can find all of those points. How do we find the scale factor based on the lengths? How do we know if it's an enlargement or a reduction? Well, we're going to find the two corresponding side lengths, the image and the pre-image. So I say, okay, here's AB and here's A prime, B prime. Okay, this is the one that it changed into. So we're going to put X over Y, new over old. X over Y, new over old. If possible, always, always, always reduce your fractions. So many people lost points on the last test because of not reducing fractions. In our example here, we have ABC dilates to DEF. Again, how do we know which sides correlate to each other if they don't have the primes? Is the way that the statement is written. We can say AB corresponds to DE because they are in the same place within the statement. The first and second letter, first and second letter. We've been seeing this over and over for the past few weeks. We're still using it. So AB corresponds to DE. If ABC dilates, that means we started with ABC. This is old, this is new. New over old means DE over AB, which is 4 over 2, which simplifies to 2. This tells me my scale factor is 2. I can always double check by saying, is the result bigger or smaller? If my result is bigger, this should be a number greater than 1. If my result is smaller, it should be a number less than 1. 2 is bigger than 1. My result is bigger, so we're good. For this next example, we have A, B, C, D dilating to A prime, B prime, C prime, D prime. So we have AD, A prime, D prime, new over old. New is the primes, old is no primes. So that's 48 over 12, which is 4. Then the question is my newer shape bigger? Yes. Let's look at the next example. For our next examples, we want to find the scale factor based on a graph, and we want to know, is it an enlargement or a reduction, so that we know if our answer should be greater or less than 1. Okay. Again, same thing as before, except that we need to look at distances here. Okay, so for number 3, the graph below shows a dilation. Is it a reduction or an enlargement? We started without primes, moved to primes. That got smaller, so it is a reduction. What is the scale factor of the dilation? This is old, this is new. Find the side that it is easiest to find the distance. If you have a side that is horizontal or vertical, use that one. If not, you'll probably need Pythagorean theorem. So in this case, we have a vertical side, distance of 2, 4, 6. Vertical side, distance of 3. New over old is 3 over 6, which reduces to 1/2. We said it was a reduction, so that matches. On number 4, we're doing something very similar. We want to know, is this a reduction or an enlargement? So no primes to primes. The primes are bigger, so this is an enlargement. What is the scale factor? This is old. This is new. New over old equals, we need some lengths. We need some distances here, okay? And I only need to find 2 of these side lengths. I'm going to choose AC because I can draw a nice triangle there. So this is 3, this is 4. Then I need to also do the same thing for A prime, C prime, because I need the corresponding side. This is 3, 6, 9, and this is 3, let me count by 2s, 2, 4, 6, 8, 10, 12. Okay, now I can find these side lengths and divide them, or I can say these 2 triangles have the same scale factor as these 2 sides, right? Similar triangles. The hypotenuse of these triangles has the same scale factor as the legs of the triangle. So I'm going to say this is my new, this is my old. 9 over 3 reduces to 3. It's an enlargement, so that works. If you use the Pythagorean theorem to find this length divided by this length, you will get exactly the same answer. Okay, let's look at our last example here for the video. Graph the composition of transformations. So first you're going to plot these points, translate it, then dilate it, be careful with that, and then determine if it's a rigid motion transformation, why or why not, and I'll see you in class.